So after we have discussed Laplace type approximation, let us now turn to methods of evaluation of the oscillatory integrals. And in order to introduce you to the motivation of this, imagine you need to evaluate some integral of the following form. And as usual, we will be interested in the limit of lambda, which is large, and for definiteness real and positive, although it doesn't change much. And in principle, would the exponential be real? We would know what to do. We would just find the points of extremality of f of x, expand it in the vicinity of these points, and this would give us a certain regular procedure to calculate the full asymptotic series. But by now, we didn't deal with the case where this integral is at the same time of oscillatory nature and determined by some inner points of the interval. You may remember, though, that we have considered actually the integrals of this form, but with certain restriction. And in particular, we discussed some cases where this integral can be estimated by integration by paths technique. So let us briefly recall it, and let us try to understand when this technique may break down. So, and the technique is actually relatively simple, as it just relies on the following set of transformations. And after this is written, of course, we may just employ the integration by paths technique. So, and of course, this procedure can be iterated again and again. And since each integration by paths of the exponential produces some power of lambda in the denominator, it means that formally this is an asymptotic series. However, this procedure is flawed for some particular case, or not so particular, when this integral is actually not so well defined. When does it happen? It happens when you see what changed after one integration by paths. We have this f prime of x in the denominator. And it is well possible that f prime of x will have a 0 in the integration range. And of course, this transformation will not help in this case because this integral will be singular for some inner point of the interval. So this particular case should be treated in a different way. And the intuitive understanding of this situation is simple. You see that in general, if lambda is large and positive, then this exponent is strongly oscillating. And most part of the integral just cancels out because of these dramatic oscillations. However, for certain points of x, and in particular when f prime vanishes, of course, these oscillations stop, so to say, for a moment, for certain small range of x. And because the oscillations effectively disappear, this vicinity of these special points may contribute a lot to the integral. And these points where f prime of x is 0 are called stationary points. Stationary in the sense that certain velocity, which is f prime, vanishes. And actually, it is possible, and in fact quite general, that these stationary points contribute the most important part of the integral. And let us consider some specific example. And before turning to this example, let us briefly recall what did we use, what facts of integration did we use for successful implementation of the Laplace method. And most importantly, we relied on some fundamental definite integral. In the most basic form, it looks like that. It's just square root of pi. And it actually can be generalized as long as certain parameter a has positive real part. Actually, the following formula can be written. And as you may remember, this was the basic building block of the Laplace type approximation, this well-familiar Gaussian integral. And it is obvious that we need some other building block for this new situation, because for us the exponential will be will not be real anymore and will not decay, but instead will oscillate. And for this situation, we need a new building block, an oscillatory integral of the following form. So note here that there is imaginary unity in the exponential. And actually, this will be our first excursion in the complex plane. And this integral can be evaluated by the deformation of the integration contour. So let us draw complex plane of x. And now our original integration path runs along the real axis. And in fact, you may know from the course on the complex standard course on the complex analysis that for such a kind of integral, the contour can be smoothly deformed as long as it doesn't pass any special points of the integrand or end, as long as the integral remains convergent in the process of such a deformation. So here the deformation is straightforward. Let us just switch the integration contour to the straight line which crosses the real axis, forming an angle of pi over 4. So this change of the integration variable is equivalent to writing x equals exponent of I pi over 4 t. And importantly, the integration measure also changes by the same factor. And as a result, we may write down the following expression. So this integral becomes exponent of minus infinity to infinity. And now t actually just parameterizes the length along this path. So the integral becomes exponent of I pi over 4 dt. This guy comes from dx. And the remaining term is very simple. It's exponent of minus t squared. And of course, here is our well familiar integral. And all difference comes in form of the complex factor. It's actually one of the square roots of imaginary unit. And this is nothing but exponent of I pi over 4 over times square root of pi. And of course, it is very straightforward to generalize this integral to include some real parameter a in the exponential. This will be by now a simple exercise for you.